This conference will now be recorded.
So very good morning to all. Today we'll be discussing some important and very interesting part of the waves chapter that is the beats, which we have already started discussing a little bit. Today we'll do detailed analytical treatments and we'll see the practical applications of beats along with few numerical examples. So let's start today's lessons. I'll just recap what we have learned about beats first. We had learned the definitions. What is beat? Actually, beat means here when two sound waves slightly having slightly different frequencies travel along the same path with same directions and they superpose each other, then the resultant intensity of the sound will vary. Sometime it will rise and sometime it will fall, and that will happen periodically. So you can see here there are two waves of having different, very slightly differing frequencies. So one is blue, another one is orange. So these two waves, they are traveling in the same direction with slightly different frequency. Now when the superposition of the intensity, or you can say superposition intensity is actually square of the amplitude. So the intensity of the sound wave, resultant sound wave, will see it will rise sometime and sometime it will fall. So it will be maximum sometime, it will be having minimum sometime. So such rise and fall in intensity, so such rise and fall in intensity actually is called beat, but it has to be periodic. So these periodic variations in intensity of sound caused by the superposition of two slightly differing frequencies are called beats. Okay, nowadays you might be very much familiar with beats because we are listening various musics while traveling with ear, earphone or headphone, etc. So beats are actually variations in intensity caused by the superposition of two sound waves of slightly different frequencies are called beats. So intensity sometime it will be maxima, sometime minimum, maximum, minimum, like that. So what is actually a called, if I say is a beat, how many bits are there? If you want to calculate, suppose here, how many bits are there from here to here? How many bits are there? So you have to count. How do you count how many bits are there? So always you remember one maxima and one minima that constitute a bit. This is a bit. One maxima, one minima. Okay, together constitute a bit. All right. So you can look here. There are there are 1, 2, and 3 bits over here. 3 bits. Okay. So how do you find out what is the number of bits? If suppose there are two sound waves having frequency nu1 and nu2, and where nu 2 is slightly greater than new 1, not much, slightly greater than new 1, then number of bits will be new 2 minus new 1. So number of bits can be found out by taking the difference between the frequencies of the sound wave which are producing bits. Okay, so that will give you number of, I'm sorry, this is not number of bits, this is frequency of the bits. Frequency of the bits. Okay, frequency of the bits. The difference between the frequencies will give you the bit frequencies of the bit. Okay, so now with this idea about bit, so since it is a periodic variations, so that will have its own frequency, that is called bit frequency, and the period which is reciprocal of the bit frequency is called the bit period. Okay, reciprocal of the bit frequency is called bit period. Now we'll do analytical treatment of this bit. So let us consider two harmonic waves of frequency. So let us consider two harmonic waves of frequencies. Nu 1 and nu 2. Each of amplitude A and angular frequency omega, and they are suppose traveling in the same direction and in the same medium. So we are just writing these two waves with frequency nu 1 and nu 2 can be written as sine omega 1t y2 is equal to sine omega 2 into t. So omega, we know omega is equal to 2 pi nu. So if we write that, we get a into sine 2 pi nu 1t. Okay, and this one a sine 2 pi nu 2 into t. Okay, so these are the things we have got, we have just considered. Now what we can do, we need to find out bits. Bits means what? Primary thing is it has to superpose. So these two waves have to superpose. So upon or applying the principle of superposition, applying the principle of superposition, So if we apply principle of superposition, then what we will get resultant intensity as y is equal to y1 plus y2. So let us write that. So the resultant will be y is equal to y1 plus y2, y where this is a sine 2 pi nu 2 into t. Sorry, this there will be sine obviously. Now see, this is actually in terms of addition. We can just use a trigonometric identity to make it in terms of multiplication, so that we can do 2a sine of 2 pi. Let us take this as common. 2 pi nu 1 plus nu 2 divided by 2, and cos of 2 pi nu 1 minus nu 2. So this is the thing we will get upon superposition. So if we rearrange this 2a cos of let us take this common 2 pi and nu 1 minus nu 2 divided by 2. So this 2 we can just get, okay, let it be there. And along with that, the sine part. So this is the equation we have got upon superposition. If we look carefully this equation, we can just say that 2a cos of 2 pi nu 1 minus nu 2 by 2, that the whole term can be thought as the amplitude of the resultant wave, and the sine 2 pi nu 1 plus nu 2 divided by 2 into t is the harmonic waves, that would give the wave part. So then we have actually two things. Let me just term this to be mode. Okay, if we say new mode, let us name this term as mode, new mode. Okay, new means frequency, new is frequency denoted by frequency, and these term to be average, new 1 plus new 2. This let us say average. Okay, so mode and average we have got. One thing, if you look in the previous slide itself, let me just take this figure in that. Let me take this figure alone. Look here, two things are there. It is acting as kind of this beats. Actually, it has two things. One is the intensity variation, and another thing is the period. So in this, you can see I have waves with very largely varying frequencies. So these are the things. So these are largely varying. So this is actually mu average. Okay, so these rapidly varying frequencies, these are the rapidly varying frequencies. They are actually called average. And if you draw a kind of envelope by just adding the tip of the wave here, look this part, this the envelope, this is actually envelope, kind of envelope, or modulator it called envelope. So this is also varying in intensity with time, you can see that. So this is also varying with time with. So this envelope has actually a great the slower frequency or lower frequency. In fact, the new mode is the frequency of that envelope part, and new 1 plus nu 2 by 2, that is called average, that is representing the frequency of the rapidly varying part. So look, you can see nu 1 minus nu 2, that is giving the frequency of envelope, this one. And this rapidly, these are the rapidly varying terms like this. So these rapidly varying terms, actually they have a later frequency. So this thing is actually represented by this mathematics. I'll write the resultant wave over here once again. So 2a cos of new mod sine new average. This is the average. I'm sorry, this let me write in cleanly over here once again. This place is small, so there's a pen is at the edge, it is not writing well. So it is 2a cos of new mode, and this sine So this average frequency is the frequency of the rapidly varying part, and the envelope, as I was showing you, the envelope has the frequency nu1 minus nu2 by 2, which is called mode. So we have learned two things: mode and average frequency. Now, what is the period of this? That period can be found out from here itself. Now we'll see few things when this is reaching maximum, when this is reaching maximum or minimum. Okay, look in the next page. So this is actually slow varying modulator part. Slow varying part, that's a rapidly varying part. Rapidly varying part. Okay, sine part is rapidly varying part. Okay, so if we take the 2a cos of nu mod, so this will be 0 if this becomes n pi. Oh, sorry, this will be a 1. Okay, we can obviously we have one more thing here. So n pi into t, there should be a t. So we see actually the time interval between, okay, let me, this t is tau over here. The t time is actually, so these are the actually time periods, 1 by nu1 and nu2. And the difference between the successive maximum and minima is actually 1 by nu1 minus nu2. So what we have discussed a little bit, let me just clear it out once again. Suppose the intensity of the rapidly growing part is 2a, sorry, slowly varying part, 2a nu mod, that means nu1 minus nu2 by 2 into t. Okay, now this can be maximum and minimum. R can become maximum when this is n pi is equal to n pi. This into t has to be equal to n pi. Here actually there should be some 2 pi over here. Okay, 2 pi also. So 2 pi. So this get cancelled here, here. So t will be n by v1 minus v2. So this is giving you a general formula for the time interval. Okay, so for the time it takes, see, this is the time. So the time interval between two successive will be, so t n by n n by nu1 minus nu2. So this n you can put 1 2 3 etc. Okay, so in that case you will get various, you'll get the this particular bits at various times. Those are given by, so these are the sequential, subsequent or successive maxima. So their maxima will happen, and see difference between the two successive maxima will be, so this is one maxima, this is another maxima. So the difference between these two maxima will be, say, it will be 2, it will be 1. So if you just take the difference between two successive maxima, that is the time when the maxima are occurring. So time delay or difference between two successive maxima are 1 by minus nu1 minus nu2. This is the time interval between successive maxima. If we put this 0 to be 0 minimum, then also you'll get the same number of same time difference between successive minima also will be 1 by nu1 minus nu2. Okay, if you take the reciprocal, then you will get that bit frequency. Okay, so these are the things. Now what we'll do, we'll try to understand few applications of bit. See, first of all, this property of bit is being used in various applications. First of all, it can be used to determine the unknown bits can be used to determine the unknown frequency. So one application is this: beats. By listening the beats or producing beats, we can use this beats to determine unknown sound wave. Okay, so how do you use this beats to determine unknown sound waves, like frequency of unknown sound wave? This is actually frequency. So, so to determine unknown frequency, you should have two tuning fork. If you have two tuning forks of slightly having, like, they can produce sound wave slightly different frequency. Then once you you can just do one thing. If you have two tuning fork, one is known one, another one is unknown. You just blow them. There will be bits produced. Sometimes bits will be rising, and sometimes bits will be lowering. So if suppose the bit frequency, sorry, then suppose the one frequency has frequency b. Suppose nu 1 is equal to nu 2 plus b. What does this mean? Suppose the standard one has some frequency, and the other one, as I was showing you, the other one will have frequency. Suppose this nu 1 minus So to determine the unknown frequency, you can use this bits method. I'll explain once again how it is. Suppose you have one sound have frequencies. Suppose sound wave have frequencies nu 1 and nu 2. And suppose one is known, another one is unknown. Suppose you have unknown frequency, you need to measure. That will be actually known frequency. So unknown frequency actually will be given by, this is plus minus the frequency of the known and plus or minus the number of bits produced actually. So we know the unknown frequency will be known frequency plus or minus the number of bits. Known frequency B, number of bits. This will be plus or minus. That means, if this is, suppose this nu 2 is unknown. So the unknown will be is equal to known frequency, suppose nu 1 minus or plus or minus B. Okay. Now if you want to consider whether it is plus or minus, then you have to just, for the case of the unknown one, you just apply or load with some wax. The prong of the tuning fork, you have to load it with wax. And now the beat you get, if that has a greater frequency, then this unknown frequency will be nu 1 plus beta, because frequency is increasing. Okay. If the frequency decreases, then it will be minus. Bit frequency increases and decreases, depending on that, or decreasing. If the bit frequency is increasing, then it will be nu 1 unknown plus B, that means number of bits, sorry, the frequency of bits. If the unknown frequency, sorry, the bit frequency upon loading the wax decreases, then you have to think, I'm sorry, there was, yes, so this will be other way around. I'll just take up an example. Let me see. So this is new one plus or minus b. Suppose I have two frequencies, sorry, one unknown frequency. Okay, you have some you have been given unknown frequencies to measure. So suppose you have a fork of unknown frequency when sounded with one frequency, new one, to be this is 288 hertz. 288 hertz gives 4 bits, giving 4 bits per second. When they loaded with piece of wax, suppose it gives the same number of bits. Suppose it gives the same number of bits. Find the unknown frequency. So when the frequency increases after filling, that will give you nu 1 minus nu. And when the bit frequency increases, then it will be plus. Okay, so 4 bits. And so suppose there is a tuning fork and a known frequency of this, and another one is unknown frequency. When this tuning fork is sounded, this frequency will superimpose and produce bit, which will give you the bit frequency. Suppose the known one is this, so unknown is 2 is equal to this plus or minus. So plus means you'll get 288, 288, so 292, or okay, or it will be 284. So which one among these two frequencies will be the unknown frequency? One is 292, another one 284. Now the problem is, if the bit frequency increases, then it will be this one. If the bit frequency decreases, then this will be the second wave. Okay, so we'll stop it here for today. We'll actually discuss in detail the mathematical part in the next class, that is tomorrow. So bye for today.